Morning. We're Team 2, and we'd like to present our awesome toy, Marstang. So basically, there's a whole backstory to this. It's the 29th century. We're deep into space exploration, and one of the things that we've gone into is Mars. But Mars is very much like the Wild Wild West now. There's a lot of different settlements on Mars, much like the American frontier. Basically, you know how the French, Spanish, British, they were all kind of competing over. Basically, the same things happening in Mars right now. But the vast and new frontier is being explored by the typical wheeled vehicles that we see here in today's 21st century. However, we have discovered new natives on the planet, much like the natives on this planet. And much like the Europeans in the 19th century, humans have decided to ravage their planet. So there's an ongoing war between the natives and the humans. And basically, but we found a different type of transportation that they were riding, which is much more efficient on rocky and sandy roads. And it's called a Marstang, much like the horses, except it's in the future. Future is cooler. So we have decided to take him over, and we decided to reverse engineer it, and now humans can ride it, much like Ken here, as he's enjoying himself. And then, like as horses, riding our Marstangs, and we will eventually conquer the planet.
Okay, that's it.
Okay.
Yeah, so the inspiration to design this toy was the Strandle Beast developed by Theo Jansen, which developed the the mechanism which achieves the walking motion of the toy. And if here you can see it's a six link mechanism which achieves the walking motion, because as the the input crank rotates, the foot, which is the lowest point of the mechanism, spends part of the rotation drawing a horizontal straight line, and then lifts and goes back to the initial point, which is much how we humans walk. So the gray, well, you can't see, behind the red links there's a crank which rotates, and by having two legs you achieve that the toy doesn't balance and it's able to walk.
So of course you got to have something to ride on when you're on a Marstang, so we needed a chair. So the way we did that is actually creating 3D geometry using flat 2D material. This was acrylic, which was laser cut, and then it fits together much like a puzzle, and that's what created the chair.
Finally, after we had the chair and the legs all decided what we were going to do, that it was a matter of designing a chassis that will hold everything together. The challenge here was to keep it under the volume SLA and keep it as light as possible. And so after that was done, it was all put together, and Kara was taking and making sure that there was as minimum friction as possible for the assembly. And here we got out the video of the actual simulation on Pro E.
Use the mouse on the TV. Play them all. All of them play.
So here the legs are showing that they're all in sync, but then we found that a better way was to offset some of the rear legs to the front legs. Now for a real world demo.
Does anyone have any questions for us? How is that powered?
Here, you can show the bottom. So under here we have it's two main shafts, and then they're connected by a belt drive, which is toothed so that it doesn't skip, in order to keep the alignment of each wheel. And then we just have a geared motor. It's a warm gear gearbox, which drives one of the shafts, and then by the belt drive it drives both. So what we were thinking is that in the future it could be done so that you have encoder, like motors with encoders on them, so you can program it to turn and do all sorts of nifty things.
Any of the toy makers making something similar to this?
Not that we're aware of.
Do you see this as a kit of parts that people assemble or pre-made?
We actually see it both. We actually were using the initial motor that we used was Connects, so we could see it actually being developed into some sort of like a Lego or Connects type of toy. It's very possible.
And did you go through, from an engineering point of view, the force, I'll get it out in a minute, force velocity calculations on the mechanism?
No, well, we didn't actually do any like extended kinematic analysis of it. We did take care of making sure that the motor would be able to turn.
And
So
since the material for the legs is not very heavy, we assumed that the motor would have enough torque to.
So we geared the motor. We found we geared it to not the lowest, but almost the lowest speed we could, so that to get the maximum torque. And again, like we did make sure that all the pins and everything were produced as minimum friction as possible.
One thing the kids like to do is to resist the force of the motor whenever they have a toy that moves. If a kid were to grab onto one of those legs, would a gear slip and the whole thing run?
Yes, the motor actually has a clutch in it built in. So we actually had it happen that one of the pins got caught on the frame, and all it does is start skipping. And then, but like everything remains in sync. It's just the actual, like inside the gearbox, there's a little clutch and it just skips.